Good morning, everyone. My name is Arup Kumar Sarkar. I am a first-year PhD student at the Department of Computer Science, University of Virginia. Today, I am going to present my rotational and research, which is incremental perception on real-time 3D data. My supervisor is Professor Felix Lin. So this is the whole contents. First, I'm going to present the introduction, motivations, and the contributions. Then I'm going to describe what is the incremental perception, and after that I will describe in details about our proposed idea. Then I will show a little bit about preliminary observations, and we have introduced some research questions, and there are some future works. So 3D vision is a very important part of the autonomous vehicles. In a 3D vision, 3D point clouds flow in through LiDAR. The data is fed to a vision-based perception module. The perception results, that is object bounding box, are further fed to downstream module, including prediction, planning, and control. The delay between data integration and control stimulus is crucial to a vehicle's safe and comfortable maneuver. So this is an overview of the whole autonomous vehicle pipeline. Here you can see that there are different sensors like radars, cameras, lidars. They capture mainly 3D or 2D data, and there will be a perception and vision module which is combined both type of data, and after that those data will generate a tracking list in the tracking module, and after that there will be some prediction list. So the output of the predictions will be used as a input in the planning module along with the localization input. And after that, there will be a motion planning for the control, and control will send those control decisions to the actuator. So there are some key challenges in the autonomous vehicle or autonomous vehicles because to get the high throughput, there is a cost, and to perform a good motion planning, we need a low latency. So there are some research like, delay should be less than 100 milliseconds to ensure safety and passenger comfort. While mass prior work focuses on optimizing 3D vision for efficiency, our key observation is that the attention over an inter 3D point cloud, which is a waste of resources. Though processing a full point cloud will increase the accuracy of the object detections, but motion tracking to keep the system in the right path has a significant overhead. So that's why the accuracy of perception fails to capture relevance to downstream tasks when the motion control depends on a highly critical task that is dependent on the latency. So here is an example. You see there are different modules, perception, planning, and control. If perception, latency is 10 milliseconds, you see at the frame 3, and data is available after 10 milliseconds. But the planning, if planning expect the data within 5 milliseconds, then there will be a data unavailability, right? So what the planning module will do here? Planning module will use the past data to perform its motion planning, and same way the control module will also perform action based on all data result. So that is why we mainly focus on working on the latency in different modules in a whole autonomous ecosystem. So in this work, we mainly contribute by identifying lack of targeted attention, which is a major inefficiency in autonomous vehicles perception. In response, we advocate for guiding the perception with feedback from the planning and prediction. Additionally, we propose a mechanism of incremental perception and priority object vectors, which allows an autonomous vehicle system to act based on an inaccurate perception with low latencies and refined perception on demand. So we also pointed out pointed out some open source questions in 3D vision algorithms, planning and autonomous vehicles job management. What is incremental perception? It is nothing but a process of taking a partial point cloud data for 3D vision to get an inexact perception, and it will increase the point cloud if there are some refinement requests come for the better accuracy. So in the figure you see for frame one are using 75% of the point cloud data and getting mean average precision is 38. So what a planning module will do, either planning module can perform motion planning if it has enough confidence or not. But in the frame true, there are 80% of the point cloud data, and the mean precision average is increased to 49. So planning module will might be perform some motion planning based on that, and send some planning output to the control module so that control module can deaccelerate the speed. But if it is needed, then at the frame 3, there will be 90% of point cloud data with higher mean precision average, although it will add some delays, but it will increase the confidence of the planning module and send the motion planning to the control unit. So this is our proposed idea. Actually, we are mainly targeting on the delays in different modules. Here we are advocating for codesigning and autonomous vehicles perception and downstream models such as planning and prediction. The idea is to add a feedback path from the downstream to perception and guide the perception with the feedback. As a result, the perception can reduce its processing delay and achieve higher efficiency. Here you see the module with the green color is our proposed module into the existing ecosystem. So what will be inside the downstream adaptation module? To realize the idea, we propose a mechanism called incremental perception, where the perception module processes a point cloud frame in multiple iterations. The initial iteration quickly produce inexact result, that is raw 3D bounding box. Based on that, priority object vector will create it at the downstream module, either take actions with lower delays or request the perception to refine the result with additional iterations. So there will be a selector, a module which will choose the frames, which will choose the frames and the other parameters from that specific perception. So this is our preliminary observations. If you see that if there are less percentages of point cloud data, the mean average precisions will be very less. So I think it is very good idea to use higher percentage of point cloud data, like here it's 18 meter, which will give you better result, and at the same time the vehicle is 18 meters away, so it will have much more time to make a good motion planning, either change trajectories or brake the vehicle. So this is also a comparison between the inflexible distance to control, which is the ideal case, and our proposed idea. Like when vehicle is 18 meters away, and at the same times, like control decision are executed after 400 milliseconds for the ideal case, right, because it is processing the whole point cloud data at the same times, so that it will only have 793 milliseconds in hand to either change the trajectory or break the vehicle. For the adaptive case, control execution are made in advance because of the partial processing. So after some times, like after 200, even 150 milliseconds, it autonomous vehicles got a minimum level of confidence to change the trajectories or a better motion planning to slow the vehicles, and even after that, the adaptive control slows the speed in advance, and at the whole, uh, adaptive control has mass remaining time in hands, which is like 1.6 seconds. Here we have opened some research questions. The number was 3D vision algorithms shall allow trade-offs of specific error types. They should support incremental computation with result reviews. The planning module should act on inexact perception and provide feedback to the perception for refinement. A vision job manager shall dynamically create and configure predefined and on-demand vision job and dispatch them to ingested point cloud frames. The OS should schedule a job graph with the circular dependency. So this is our current status of the work. We have submitted this work to Automobile 2022 on 6th November 2021. Currently, it is on review stage. We are hoping it will be approved, accepted. Yeah. So there are some future works there. We have also planned to add additional downstream adaptation module between planning and control to get better motion planning. We also can optimizations in the aggregation step when we process the point cloud in the perception stage. And at the same time, we can also introduce additional priority object vector in between planning and control to save post-control actions for better motion planning. So in this work, we presented an adaptive motion planning and control process, an additional planning method for autonomous vehicles. We showed that the process of inexact perception contribution to generate priority object vector, frame selection in perception refinement request, and constraints of processing it in multiple runs. We believe our proposed method about adaptive incremental point cloud data provides a better insight for further research on motion planning and control in the whole ecosystem of autonomous system. These are the reference. I hope you enjoy the presentation. Thank you.